thanks again for the introduction, Jans, and again to the association for hosting me today. So this is the third part of the overall training of today with regard mainly the application to a case study. So initially, when we were thinking about this course, for which I still want to thank Normund for the idea, we were thinking about presenting some simple design of simple structures. I was thinking about this structure that was really designed in our campus by me and our group, originally steel, but it has been redesigned in concrete for this example. I want to underline that if it is of interest in the future, we can try also to plan to prepare other case studies, structures, based more on typologies which are closer to your practice. So this is, let's say, just an example. We want to look mainly at the principles rather on the specific case study, let's say. So again, just to connect to the previous discussions we had, I want to say that, of course, when we are dealing with seismic design, we can, in some cases, still think at designing structures. I don't know if you see this bar. You see it? Maybe yes. I'll move here. Okay, sorry. I moved the bar. I had a bar from Zoom.
We didn't see nothing.
Okay. So it's okay. So I wanted to say that mainly we have to deal with ductility because, of course, in some simple cases, we can still follow the idea that we designed the structure to be fully elastic. But this is normally not very efficient in terms of costs because, as you see, we have to design the structure for higher forces. Designing for higher forces means, of course, having elements which are larger, so cross-section which are larger and costs that will become higher. So in some cases, it is still possible for simple concepts or simple structures like single-story building, industrial buildings, or buildings which have a low mass, like some type of wood construction. But in most of the cases, we will have to deal with ductility. So we cannot avoid to do it. So why is this important? It's important because, as we said, we need somehow to dissipate this seismic energy. And of course, this energy will be redistributed within the structure in terms of damage. So we have to activate some plastic areas, some critical areas, some areas where we allow to have some damage. And therefore, we have to decide and control. So let's say, if you want, this is a control damage approach. So we control the way the structure will damage under a seismic event in such a way that is able to provide a sufficient performance. So what are the factors which are influencing the ductility? This slide I'm referring to reinforced concrete, but I will tell you some very small things related also to steel structures. Basically, when we are dealing with RC structures, this is dependent strongly on the way we design the elements and mostly the way we arrange and place the quantity of reinforcement in terms of bars, but in terms also of transverse bars. So also we will see it is very important to perform a very clever design of the stirrups in regards to the shear. We will always deal with concepts which are related to hierarchical design, as you see highlighted in this slide. So hierarchical design, it means that somehow we will have to decide in our design what are the elements to which is entrusted the energy dissipation, and all the other parts will have to be designed to have some kind of overstrength. So we will see this in more detail in this presentation with the application to case study. So we have 4 types of ductility. So ductility, this is what you already know for sure, can be the ductility of the material. So steel or concrete can have some ductility, especially steel. We will exploit typically the ductility of steel parts and also of concrete. And mostly this ductility, if the material is ductile, it will be possible normally to reach also a ductility that we can regard at the level of the cross-section. So This will be, as we see, a ductility expressed in terms of curvature. So higher curvature will mean higher ductility of the cross-section. Going at the upper level, the ductility will be possibly the ductility of a member. So a beam or a column. So to have a ductile member, we must have a member which is done with a ductile material with a large local ductility in terms of curvature. This ductility, so normally we think at members which are forming plastic hinges and the ends, will be translated in terms of rotation. In terms of global ductility, the global ductility will be regarded as the capacity of the whole frame to survive, let's say, to a lateral displacement. So it is important to remind that there is no global ductility if there is member ductility, there isn't member ductility, local ductility, or material ductility. All these aspects are interconnected. They are not independent. So this is summarized also here. So let's say that we have a frame. Of course, we can have more advanced strategies like dampers, but in the typical case, we will work with hysteresis. So let's say that the idea is that hinges will form in the beams, for example, in these areas, this location. The ductility will be, at the global level, the capacity for the structure to have a large displacement here at the top story for a given base shear. This large ductility will be possible only if this plastic region will be able to rotate. So this is, for example, could be the moment rotation or force displacement here in this written diagram of a plastic hinge. The frame ductility, so the global ductility, depends strongly on the failure mode, so on the capacity of the structure, and this depends on how we are designing the structure, to redistribute the actions and to have a certain level of redundancy, so to form, possibly, a larger number of plastic hinges. So here you see compare a story mechanism, so a failure mode which is seeing the failure of just one story of the building, in this case the base, which is very typical to have a weak base story in non-seismically designed building. And this is compared to what we normally call the global failure mode, where we form the maximum number of plastic hinges before achieving a failure mode. In this case, as you see, while in the upper diagram we have just 8 plastic hinges, in the lower case we have a number of plastic hinges which is 6 per story times the number of stories, so it's 24, plus a plastic hinge that will form at the base of the columns. So we have 28 plastic hinges. So increasing the redundancy and the possibility to redistribute the actions will allow, in any case, to have a larger drift, which can be reached with the same rotation of the plastic hinge. This will give a very high possibility of dissipating energy. So, as I've said, these are not separated aspects, so the possibility for the building to reach a large lateral displacement even with damage, so the global ductility that will be expressed as the global displacement at the ultimate and in the yield condition, will be dependent on the member ductility, so the possibility for a member with plastic hinges to rotate, so for the plastic hinge to rotate. This is expressed normally the ductility in terms of rotation as the ultimate rotation of a plastic hinge over the yield rotation of a plastic hinge. But this will be dependent on the ductility of the cross-section that will be regarded as the ratio between the curvature, that is the slope of the strain diagram here, and the ultimate condition, so when the concrete, for example, is failing, and the curvature that we have at the yield condition. So, for example, when the bar is first yielding. And this section ductility will depend on the material ductility. So, the capacity for the material to have an elongation in plastic range. So, the ratio between the ultimate strain and the yield strain for the material. All these 4 aspects have to be controlled by us. Can look very complex, but this is what we will do with the application of all the design rules that we will see today. So when we are talking about the material level, and concrete. So today we're talking mainly of reinforced concrete, and I will say something about steel. In reinforced concrete, and so concrete, we know that it is possible eventually to activate a larger ductility when the concrete is confined. So, So concrete confinement is a key aspect. So it is increasing the compressive strength of the material a bit, and mainly is increasing the plastic behavior of concrete. So the capacity for concrete to have a deformation in plastic range. This is why normally, due to this beneficial effect of plastic hinges, we will see that we have a certain of rules which are about the minimum reinforcement in terms of bars, so longitudinal bars, but more important, in all the areas which have to be ductile, which are basically the end of the beams of the base of the column, we will have certain rules about the pitch or the spacing which has to be respected for the stirrups. So all these rules about minimum bars and minimum spacing for the stirrups are basically related to the idea that we want to have concrete which is confined. Confined concrete, like the diagram here is compared a confined and unconfined concrete, basically will increase a bit the strength, but mostly will increase the ductility of the material. Of course, in reinforced concrete, we don't reach high ductility of the cross-section mainly because of concrete, also because of concrete, but specifically we try to exploit the energy dissipation capacity of steel. So in concrete, basically, this will be due to the possibility to have an elongation in a bar as large as possible. In a steel element, like a steel beam, this will be due to the capacity of the beam, so the deformation of the material which is composing the beam. So when I'm talking about steel, here now I'm talking a little bit in general. This can be concrete, reinforced concrete, this can be properly a steel structure. Of course, what we don't want to have is to have a brittle failure mode. So we don't want that as long as we achieve the yield strength of the material is breaking. Steel is the perfect material for dissipating energy because we know this material has a very large elongation in plastic field. But we have to take care about two aspects which are highlighted in this slide. When we have to design a structure to have a certain hierarchy in the elements, so for example, if we want the beams to be the weakest element of the structure compared to the columns, we have to remind that to design the elements, it will be needed to make proper consideration for these two factors that we see here, the randomness and the strain hardening. What I am meaning with this? If we are used to make, let's say, a static design of structure, not for seismic, typically what we control is that the stress level is equal or below a design yield stress. So normally I'm checking that the steel member or the steel bar has a stress which is not going over beyond a stress level. So that here is indicated as the design yield stress. But if a part of the structure has to undergo some plastic engagement because this is what I want, this is desired, let's say, in a seismic situation, I have to consider that really the real resistance of the material will not be the design value, which is reduced by some safety factor. It will be the characteristic value, but in reality it can be even larger because typically it will be closer to the average value, but in any case, this will be related to some statistical concept. So, of course, if I am designing a structure with bars, steel bars, which are belonging to the class B500, so they have a yield stress of 500 megapascal, I know that in reality, this is the minimum guaranteed value. But in the real structure, this steel will yield for a higher value of the stress. So I have to remember when I'm designing hierarchically, so when I want to design some structure, some part of the structure to be weaker than another, that at the material level, the stress depends, the real stress I have in the elements is not the design stress, is normally higher. It will be depend on a statistical variation. So first of all, the fact that I have safety factor. So the characteristic is the minimum guaranteed. In reality, it will be even more because there will be statistical variation of the material properties. In reality, I have also strain hardening because if I'm exploiting the ductility of the material, normally the stress level will be even higher. Depends on the point of this stress-strain law where I'm stopping. In the worst case scenario, it will be, for example, the peak of this curve. So, in the practical design, we see that for the design of all the elements of our structure, normally we don't use the characteristic yield stress, we don't use the design yield stress, but we will use this value factorized by a safety, let's say, an overstrength factor that if you want, you can see also as a safety factor. So in the hierarchy of the design, some of the parts of the structure will be designed to have some overstrength. This will be needed to be sure that hierarchically the steel material will be the weaker part of my building and only in certain areas, such as, for example, in a frame, the beams. If we move from the material level to the cross-section level, it means, so we have certain checks in Eurocode which are devoted to control the ductility, so to compare the ductility demand, so similar to what we do in a resistance framework. So you're used to compare a design action, a design force, with a design resistance. So we compare demand and resistance normally. In this case, we will see that we have certain requirements which are asking us to compare the ductility which is imposed by the seismic event versus the ductility of the cross-section. So here it is an example. This is an example of a very simple concrete beam, cross-section, let's say, not beam. Rectangular with two levels of bars in compression and in tension, are made of the same material, of course. We see that given the position of the neutral axis, we are able eventually to calculate this position of the neutral axis, by means of a translational equilibrium at failure. Focus 1 second on this diagram to highlight first a very important property. So one thing that we notice is that if this is the position of the neutral axis, so the depth of the neutral axis, typically this angle, the angle of the strain diagram, which is the curvature of the cross-section, will be larger normally if the neutral axis is lower. So if I'm limiting in design the depth of the neutral axis, I will be more directly or indirectly able to control the ductility of the cross-section. Let's look again. Sorry, I wanted to focus on this. So let's see this cross-section. Let's assume that we are making a translational equilibrium in the failure condition with the bars both yielded in the compressive and tensile area. This will be the expression of the neutral axis, y, c, is called in this slide. And let's introduce these non-dimensional parameters, omega and omega first, which are the area, so the tensile strength in the bars in the compressive or tensile region divided by the compressive strength of the whole cross-section. So the ductility of a beam will be expressed normally as the ratio between two curvatures. So this is the curvature at yielding. This is the curvature in the ultimate condition. In the ultimate condition, the curvature will be expressed by the deformation at failure of concrete, so this deformation here, over the depth of the neutral axis in the failure condition. So if I use the previous expression to express the neutral axis, I can also write this equation here. In terms of yield stress, normally this is the yield condition of a cross-section is reached because of the yielding of the bars. So if y sub c e is the neutral axis in the elastic condition, I'm also able to express the curvature at the yielding. As I said before, the curvature of a cross-section, regarded here, is the ratio between the ultimate curvature and the curvature at yielding. So with all the assumptions which are made in this slide, so let's say that the neutral axis in elastic range is about 0.25, 0.3 D, which is typical for seismic design, we see that we are able to define an approximate equation to evaluate the curvature of a cross-section. 0.51 epsilon cu over epsilon sy times 1 over omega minus omega first. So we see that the curvature depends on the ratio between the deformation at failure of concrete, which can be improved by means of confinement, for example, the deformation at yielding of steel that normally I cannot vary too much, but is depending also on this difference. So the difference between the percentage of, let's say, the mechanical percentage of bars in tension and the mechanical percentage of bars in compression. So as you see here, normally, if I'm increasing the bars in compression, I will be able to increase the ductility of the cross-section. So it's a simple example, and also there are a lot of simplification in this example, but it is highlighting an aspect which is very important. So in concrete, if I want to increase the value of the ultimate curvature of a cross-section and therefore the rotation capacity of a beam, making this beam more ductile, I have two different things to be considered. First, I have to improve as much as possible the confinement of the material by means of stirrups. So in critical region where I have plastic ridges, I have to increase the number of stirrups, not because of the shear strength, but because of confinement. Same thing applies for the compressive reinforcement. There are indeed, in codes, certain rules to increase the percentage of bar in compression in the critical region. You see in this diagram here a comparison between different situations, so a moment curvature diagram of a cross-section, considering different percentage of bars in compression. Normally, the higher the bars in compression, the higher will be the ductility of the cross-section. Okay, so it is from the conceptual point of view, I'm more interested about this. It is important to understand why we are applying these rules. So why I am having, we see in the critical region some stirrups, or why I have to improve the number of bars in compression. So these rules are normally rules which are indirectly connected to the idea of having a certain ductility in our cross-section. If I'm talking about steel, just let me say some word about that. It will not be the topic of the case study. In steel structure, it is the same concept, but I want to say this just to highlight that independently from the material, all the design rules for the seismic resistance are oriented to reaching the same objective. So ductility of a steel structure, the global, will be covered by the ductility of a cross-section. Typically, in steel structure, it will be, for example, the failure of the beam end. In this case, this ductility is not controlled with the same rules we have for concrete. Of course, there is nothing to confine, there are no stirrups. It will be controlled by means of the concept of cross-section classification. So trying to have beams which are composed by profile and cross-section which are of a higher class. Higher class for us means a cross-section which has higher rotational capacity. So you see that for steel, there are certain rules that based on the ductility class that we are assuming in design, and so the Q factor, it is allowed to use or not certain type of profiles. Normally, slender profiles are not allowed for seismic zones. Normally, class 1 profiles are the best because, of course, they provide higher ductility. 2 or 3 can be used under certain circumstances, as you see highlighted here. In concrete, as I said, this is what we are targeting, a failure mode of global type. This will be possible also thanks to the rotation of the cross-section of concrete. So we have to expect at the end of a seismic event, typically we have a pattern of cracks in the tensile region of beams. We have crushing of concrete because of the compressive forces. And most of all, we have to remind another thing that in the past was a little bit forgot in seismic design. So the importance of this critical region here, so of the panel zone, let's say, of the column, which is subjected to high shear forces. we see that we have a number of requirements also for the stirrups in the nodal region, because the nodal region is the area of transfer of the forces from the beam to the column, and vice versa. So here you see two examples. So this is, let's say, a case where we have the formation of a plastic hinge in the beam, so in this region. Obviously, depending on the direction of the forces, this is, for example, represented with these bending moments, we will have compressive forces in concrete and tensile forces in the bars. These forces result in shear in the shear panel, but the shear in the shear panel, basically, what is that? It is a tensile force in a diagonal or a compressive force in another diagonal. So we see that there are certain strata and time model that we can use for designing the plastic hinge region and mainly the nodal area. Of course, we have to avoid to have this kind of failure. So the failure of the concrete region, of the nodal region. So in the idea of having a hierarchy, the node should be more resistant than the connected beam. This because typically the hysteretic behavior is characterized by higher possibility of dissipating energy. Okay, so the energy dissipation is typically better if we are dissipating in the beams. If the structure is made of steel, like you see here, we have in reality compared to concrete different concepts. So it's possible to dissipate in the beam, as you see here, but it's possible to dissipate also in the joint. As currently this second approach of dissipating in the joint will be it will be considered in the new version of Eurocode 8 more thoroughly, more in depth. In the current version of Eurocode 8 is not actually easily possible to apply. So you see already what I will say also later. We have to establish a hierarchy in the structure. So the concepts are, let's say, the most common is this one, having a weak beam, so dissipating in the beam, but a strong column and a strong joint. So when I'm designing the structure, this means that I will start normally from the design of the beam, and afterwards I will design and check all the other elements of the building, so the columns and the joint, to be more resistant than the beam. We are talking today mainly about a frame, but let's remind that there are certain other typologies. So normally in frames, we are dissipating in the beams. In a concentrically braced frame, normally we are dissipating in a brace. Into an eccentrically braced frame, if we are talking steel, we are dissipating in a seismic link. These two concepts are not very much applied in concrete, but in steel structures for sure. You should see also, let's see, is this moving? Okay, a video. Okay, which is showing how the different concepts are applied in seismic design. Okay, so the energy dissipation is entailed to certain elements. These elements have to be hierarchically designed. This is the idea. So, concept which I have already underlined, if when I go to the structural level, so if my plastic hinges are able to sufficiently rotate to have some relative rotation in between the beam and the column, so a rotation that I'm calling here theta, at the point of the global hierarchy, the global level, the level of the structure, you see that for the same rotation, it will be possible to reach different lateral displacement based on the pattern of plastic hinges. Normally, I'm trying, when I'm designing, to go more towards a global failure mode. So a failure mode which is entailing a high number of plastic regions, which are in the beams and at the base of the columns. Okay, so to improve the global ductility, we have to select case by case, the most favorable failure mode. This to guarantee a high global ductility thanks to the exploitment of the local ductility. This is what we want always to avoid, and the rules that we applied are precisely done to avoid this. A failure based on a story mechanism. Okay, sorry, now it's running. Okay, so this is a failure mode that is very typical of buildings which are not designed compliant to a seismic code, or buildings which have irregular placement of the claddings. So in the past, of course, it was frequently found in the design to have masonry claddings in all the story, but having a free space at the base of the building. This is for sure very, very bad, because in this case, it is increasing the ductility demand just in one story. And possibly this ductility will not possible to be sustained by the elements. So now we have to talk about what are the principles, and then we see how we apply these principles. So let's say that normally in design, we start from the design seismic event, which is the one for the life-safe scenario, so 500 years. We will design starting from an elastic design spectrum divided by Q factor. So an inelastic design spectrum, what we normally call an inelastic design spectrum. We have two principles that we will always apply. So ideally, we will design the structure to have some hierarchy. How do we define the hierarchy? So we have to be clever here, because we have to think as a matter of principle, first of all, as a seismic engineer, what is the part of the structure for which is most favorable to have to have a concentration of the plastic demand. So what is the region of the structure which I want to be my ductile element? So if I'm talking of a moment resisting frame, as I said, it can be ideally the beam, the column, or a joint. But I have to consider that to promote a failure mode of the global type, I have possibly to concentrate damage in the beams. So the idea of the hierarchy is that I have a chain of elements. So let's say the column or the joints and the beams. I select initially what is the element which has to provide ductility. I will design the structure in such a way that this element is the less resistant is less resistant than the other element, while all the other elements, which are brittle, so are not able to provide a significant energy dissipation capacity, will be designed to be over-resistant. Okay, so the idea is of this chain. So the ductile part has to be also the part that hierarchically is governing the resistance of the structure. So the one with less resistance, if we can say in this way. So the principles are two. So as the first principle, I have to design with the design-based earthquake the dissipative part, the beam. So my design will start from the design of the beams. Consequently, we will see that according to the second principle, to apply this hierarchy, we will not design all the other parts of the structure for the action which are deriving from the seismic load combination, but we will apply some magnification factor, so some overstrength, that are needed to be sure that these elements are not providing any contribution to the ductility and they are not failing before the beam. So the beam is hierarchically my weak element. It will be designed for the seismic forces, but all the remaining part of the structure will be just designed to be more resistant than the beam. So it is not the typical, I understand that maybe at the beginning can be complex, because it's not the typical design approach where I take the action and I design the elements. In this case, I take the action, design the ductile elements with the action, and all the other parts of the structure are over-strengthening. So I will take the design action, but this will be increased, they will be magnified. What are the typical combinations that I have to consider for a building in seismic area? Of course, I have the typical service loading condition, ultimately mistake loading condition for gravity loads, to check deflection, vertical deflection, control the stresses if I have some stress limitation check or cracking, or the resistance of members and the stability if I'm in the ultimate limit state. But I will have for sure to consider other, so the exceptional action, so the accidental action like the seismic event. Particularly, I will consider, first of all, the design-based earthquake, the one with 475 years of occurrence. For this earthquake, on the performance-based design approach, based on, since I want to design the performance, in this situation, I will have to check the resistance of the members, the stability, but I will have to design the ductility and use hierarchy design principles. Then I will have a serviceability limit state check to be done as well. So, controlling that the lateral displacement of the building, so the drift of the building, is limited. So basically this is a control, indirect control on the damage. So there are a number of elements in a building which are sensitive to lateral displacement: the claddings, the partition walls, the furnitures, machinery, whatever it is inside. This damage will be controlled, reducing the possibility to have large sway displacement. So the displacement have to be limited within certain boundaries that were listed before by José in the previous presentation. So typically, if this is the design force in the seismic loading situation for the serviceability limit state check, let's say, so where I'm checking displacement, will be the same force reduced by a factor that I'm calling Ni. In Eurocode, this Ni factor is equal to 0.4, 0.5 based on the cases. Okay, so the forces will be lower and I will check the displacement. So as a general concept for the seismic design, first of all, I will have to define the loads on the elements. I will have to individuate in the structure who are the secondary members and who are the primary members. So for me, the secondary members will be the members that are mainly designed to carry gravity loads, but they will have to be able to follow the lateral displacement of the structure under a severe seismic event. But still, they will have mainly to carry the gravity loads. The primary member, on the contrary, will be the members that will be designed specifically for the seismic resistance. So even if conceptually can look a bit heavy to design a structure in seismic area, we have to remind that a certain number of elements, for a certain number of elements, we can simplify the design steps, because for secondary member, we don't have to comply with all the detailing rules that we have for primary members. So there are a certain number of clauses and aspects that will be needed to fulfill for primary members that will be not needed for secondary member. Then I will perform a structural analysis to assess the overall response, the actions, and so on. And then I will have to design according to the rules that we see: stiffness, strength, and ductility. We have initially to conceive well the organization of the structure to be possibly regular in plan and elevation, and to provide similar resistance in two main directions, as José said, because if we are conceiving in the beginning the organization of the structure in a poor way, it will be very difficult to mitigate these flaws at a later stage of the design. So also a little bit of experience will be needed, but this is very important. Of course, if the structures start to be very irregular, this is the reason that, so this is one of the things that always happens because of architects that are asking for strange layouts. Normally, the overall cost will also increase because I will start to have unbalanced forces, and it will be very, very difficult to reach an economic design. These are the 8 steps I tried to list for the design of a typical reinforced concrete moment resisting frame. Similarly, I could make a list for other typologies. There wouldn't be much a difference. Okay, so sorry. Sorry. Yeah. Okay, I'm here. So there are 8 steps I tried to list. So first of all, as I said, we have to design conceptually the structural scheme, divided members in primary and secondary. Then we will have to initially pre-design the members, beams and columns, because otherwise we are not even able to perform a structural analysis, because we have to know that the result of the structural analysis are strictly dependent on the stiffness of the elements. So we will have to define initially a tentative size for the beams and the columns. Afterwards, I will provide you some indication about the structural analysis for the relevant combination. When we go into the design of the elements, we have to follow this order. First, we will design the longitudinal reinforcement of beams, so the bars, so to provide the bending resistance. Then we will design the stirrups in the beams, respecting the so-called shear bending hierarchy criterion. So, as I explained, we want to avoid to have any shear failure in the beam before the full plastic development of the plastic hinges. And then we will continue in this way. So we will pass to the columns to design first the longitudinal reinforcement. So we will give some overstrength to the columns respecting the so-called beam column hierarchy criterion. Then we will design the stirrups in the columns and the stirrups in the joints. So let's say that starting from the beam, we will see that going in this direction, we will apply more and more overstrength to the elements to be sure that these are not failing. So this is a, let's say, graphical summary of these rules. So initially, I will pre-design the primary members to promote ductility. Let's say that the most simple way to promote ductility is to limit the position of the neutral axis in the design phase. So I can apply certain rules for the design of the cross-section based on the estimate of the initial bending moment, imposing that the neutral axis is limited, typically in between the range 0.15, 0.3 h. So the depth of the beam has to be sized in this way. This will allow me to easily fulfill this control on the ductility. For columns, similarly, I will have to limit the position of the neutral axis. Typically for columns, since we have only a critical region in the column, the criteria can be relaxed a little bit. So the neutral axis can be limited to the range 0.2, 0.4 h. This we see results basically if we apply the design rules in a limitation of the average stress in the column in between 0.15 and 0.3. This is not a design rule which is given in the code. This is just my suggestion to easily fulfill the ductility checks, as you will see. So then we will design the beams. We will simply do the check as we do for any other structural element. So we compare the resistance versus the action. That's it. So we design the layout of reinforcement according to this criteria. Remind that in the beams we have the plastic hinges and the critical region. So all the other things that we do in design starting from this point will be devoted to achieve ductility. So we will apply first of all for the shear layout, so for the shear design of the beams to define the layout of the stirrups of the transverse bars, we will apply the so-called bending shear hierarchy. So I can understand that maybe this can look strange to you, but for the design of the beam, I will not look anymore at the shear diagram. I will derive the shear diagram based on the equilibrium. On the equilibrium derived in the failure condition. So when the plastic hinges are formed in the beams, and therefore I have the bending resistance at the end of the beam, not the bending action, the bending resistance. So the design shear force will have to be, the design shear resistance will have to be minimum equal to the design given by the gravity loads in the design load combination plus the sum of the plastic resistance of the beams connected, so on the two ends, divided by the span, multiplied by an overstrength factor. This overstrength factor, let's say it's a kind of safety factor which is considering the strain hardening and randomness of the material. Okay, so in this way, I will be sure that the beam is not failing in shear before failing in bending. Shear is considered a non-ductile failure mode, so a brittle failure mode, I have to avoid to have failure of the element in shear. This is the idea of this principle. For the critical zone, I will provide you a list of indications. We have to place even higher number of syrup to guarantee confinement. For the columns, I apply what is called the beam column hierarchy criterion. So I continue to increase the resistance of the elements which are coming after in my hierarchy. So the beams, the shear syrups in the beams, and now the resistance, the flexural resistance of the column. To be mainly to avoid to have this kind of failure mode, this is the criteria which is used. So having columns which are more resistant than the connected beams. This is normally achieved by rewriting an equilibrium of the joint, not starting from the design actions only, but using here, you notice this is not the action coming from the analysis. This is the resistance of the beam magnified with an overstrength. So while this is the action in the column coming from the analysis, alpha will be a magnification factor of this action based on this ratio. So the higher will be the resistance of the beam and the overstrength, the higher will be alpha. So this number, as you see, is equal to 1.3 as given in Eurocode. Notice already one thing, that if I want to limit the cost of the structure, it is very important, I go one step behind, that when I'm designing the longitudinal bars in the beam, I don't have to put too much overstrength in the beams. Because here the design will become hierarchical. If I'm increasing the reinforcement and the bending resistance of the beam, this will result into hierarchically an increase of the syrups, an increase of the size of the columns. So the more the beam will be resistant, the more will be the resistance I have to provide to the non-dissipative element of my structure. Then, if I'm continuing, when I'm passing to the column will not be designed for the design shear, so the one coming from the structural analysis, but for a shear which is deriving from the condition where I have eventually two plastic hinges forming at the end of the column. Okay, I want to avoid, even under the most severe circumstances, that the column is failing its shear. So this is the idea of having a hierarchy. Last but not least, I will have to design also the joint according to a hierarchy. Normally the joints will be designed to be sure that the maximum shear that I have in the joint region will be the maximum shear resistance of the joint region will be higher than the shear demand that I have when the bars are yielding. We have certain rules. I will try to make a comment and show to you later in this presentation. The idea is that we don't want to have this kind of failure mode that you see basically here. Okay, then we have a number of ductility checks which have to be fulfilled for the beams and for the column, for all the regions which have some ductility. I will not focus too much on this in this presentation, but I will provide you the slides which are explaining this in higher detail. Okay, so remind that I was talking up to now about the primary seismic members. For the secondary seismic members, normally it is required that these elements, which are mainly carrying the gravity loads, are checked basically considering the deformation of the structure in the seismic design situation, controlling that the action in this seismic load situation will be not higher than the resistance. So for the secondary member, typically I'm not applying any detailing design rule. I will just have to control this ductility, but I will make most typically control which is based on a resistance control. So I will check shear and bending. The damage limitation stiffness was already explained by José. It is a control that the drift in the seismic loading situation is lower than a certain limit. So this is, let's say, a control which is basically related to the design of the stiffness of the structure. In case of reinforced concrete building, typically we don't have big problems of stiffness. This is more important, let's say, for steel structures. Now let's go to our case study. I will try to explain all the steps of the design. So let's say this is our site in the campus of the University of Salerno that you see here in this image in the northern part. Our destination for this building is we have a floor which is a laboratory, a floor which is an office. So this just to define what are the live loads. And we have a very simple layout for the building. So this is just a rectangular shape. If I remember well, is around 25 meters by 15. So it's about 400 square meters. We have, let's say, column that can be placed. Afterwards, I have a structural scheme. By the way, they are placed in this way. So we have 5 columns. This building was originally designed in steel. This is why you see depicted the steel columns here in this architectural drawing. But let's say that the grid of the structural elements is 5 columns by 3. So it's 15 columns. Of course, all the elements are connected by beams. These are the facades of the building. So just to give you a layout. One thing that I didn't say, sorry, is that the stairwell we will consider separated from the remaining part of the structure. So as you see here, this is a very wise option in case of seismic design, because if I'm realizing the stairwell using, for example, a concrete core or something very rigid, this will be very eccentric compared to the center of the mass of the building, creating an eccentricity that will lead to an irregularity, resulting in a torsionally flexible layout. So the stairwell is disconnected from the remaining part of the structure, this to improve the seismic performance. These are the cross-section. This is just a layout of the stairwell. Okay, we don't have to focus too much on this. Just 2 words about the characterization of the soil. So we are used to make the typical soil inspection. So these are some of the results, for example, for this case study. So let's say that we have a soil that for the first meters is filled dirt, and then we have sand gravel from 5 meters on. Let's say that we have 2 drillings to inspection. We have extracted samples to perform the geological investigation in this point, and also this other point that you see here, which is more or less confirming what we observed in the first drilling. But what I wanted to say is this one. When we are in a seismic region, one of the investigations that you have always to remind is a seismic investigation of the soil. So typically we can use, and this is not the only technique, the multi-channel analysis of surface waste. This is what is normally done in Italy, for example, because this is a pretty easy technique and cost-effective. As somebody said this morning, the idea of this soil investigation is that basically it will allow us to characterize the soil in a class from A to E, or S1 or S2 in the worst situation. So this is needed to characterize basically the shear wave velocity in the first 30 meters of the soil to make an average and determine what is the soil class. So the technique is based mainly on the I have no idea if it is very much used in your country, but maybe it already is, so there is no need for me to explain, but I give just some time to explain this thing. So the technique is basically applied using geophones, which are located on the soil, and basically a hammer is used to generate surface wave in the soil. So the result of this test will be based on the dispersion and evaluation of the data, a map of the shear velocity within the soil. So for this example, for instance, this is what we get. So this is a diagram of the shear waves velocity in the soil in the first 30 meters, as you see here. This investigation is confirming basically in terms of soil typology what we have observed before. So we have a layer of fill dirt for the first 3 to 5 meters, as we will see also in the next slide. And then we have a soil which is of better quality. So if we know what is the position of our foundation, of course, we have to consider that to characterize the soil effects and the side effects, it will be needed to define the position of the foundation to determine what is the average shear wave velocity. In this case, our foundation, as we see, is placed more or less at 5 meters depth, and therefore the shear wave velocity is in this range. So it is within 360 at 800 meters per second. So this is a cross-section of the building with the two soil inspection, and this is the seismic characterization. So, okay, so the soil, as you see, has a kind of slope. It is decided in this example to remove part of the ground and basically pose the foundation at this level. Just the data as a commentary. Basically, the weight of the building in reinforced concrete that we will design later on has a weight which is lower than the weight of the soil which is removed. So the foundation is basically totally compensated. So we don't expect to have any problem, geological problem, even because the soil is a good quality, but also in terms of deformation, because basically what we are removing is what we are putting again on the soil. So these are the geometrical characteristics of this structure in height. Let's say that we can say, I'm not reporting explicitly the checks, but based also on the layout of the structure that we decide to realize, the structure will show to be regular in plan and elevation, so that we can apply the equivalent static force method, so the lateral force method provided by Eurocode. For this example, I decide to keep these columns, so the one where you see the red line, as primary columns. All the other elements, and also the beams in red, will be the primary beams. All the other elements will be secondary beams and secondary columns. So the 3 internal columns for this example will be designed to be secondary elements. Okay, so these 3, 7, 8, and 9. We will have to check, of course, that these columns are not contributing too much to the stiffness of the structure. This is the plan, let's say, schematic plan view of the 3rd floor. So pay attention to this slide when it's written floor 1 and 2 or floor 3. Okay, so these are the material that we have decided to use for this application. So concrete 3545 and bars B500. So in Italy, we are not used to use this kind of steel. So I adapted a little bit the design to this steel because we use 450. But more or less, I would say they have similar characteristics. So when we think at the structural organization, so you notice that I already decided to put 2 frames in 2 directions of the building. I want to underline, especially because mainly, probably you are used to design building in non-seismic area. It is always necessary to have a clear seismic resistance system in 2 directions of the building. For instance, if I look at the Italian experience, I can say that before the seismic codes, so the first more clear seismic code in Italy was introduced in the 80s. This was the typical layout that we have in a building, because the buildings were designed for non-seismic conditions. So we had basically frames just in one direction, this one, and floor applied on the frame in this direction. So unidirectional floors. This is a very bad seismic arrangement of the resistance for the building, because if we do in this way, basically we don't have almost any seismic resistant element in this direction, in the north-south direction of the building. So the resistance is unevenly distributed, and this is for sure not good for the seismic behavior. When we design a frame, a reinforced concrete frame, let's pay attention a lot to where we decide to place hidden beams or dropped beams. Why? Because the inertia of these 2 elements is very different. So even if I have frames in this direction and I have beams and decide to put beams in the other direction, let's consider that if these beams are hidden beams, they will not provide much better result than before. So the hidden beam will not provide such a high stiffness to lateral loads to be considered as a seismic resistant element. So there is a bit of decision that has to be done when you start to define the arrangement of columns and the arrangement of beams in your layout. So looking at the plan view, typically it's important to decide if the column is oriented in this way or in this way. Clearly, the second, so the one more on the right of this slide. So putting the column, so if this is, let's say, the direction of the seismic forces in the direction of the minor axis, so the direction of lower inertia, will not provide a big contribution to the lateral resistance of the structure. This layout, of course, has to be considered better, much more effective in terms of seismic resistance. The same thing for the beams. So if I'm using hidden beams, typically a frame with hidden beams is not providing a big contribution. So let's say that the lower seismic contribution will be given typically by this layout, where I have the column in the minor axis direction and hidden beam. The best will be given by this layout, where I have the column oriented in the major axis and the dropped beam. In this third case, normally I even don't have a very big seismic resistance. Mostly I will have just a contribution in the second and third case for the first story. So for the first story, so if the building is not too high, maybe I can still have some contribution. But if the building has a higher number of stories, let's say that the contribution will be very, very limited. So this to say that, okay, sorry, in this slide I have some explanation which I just said to you. So if I have to choose, possibly a seismic resistant frame should have columns oriented in the direction of the seismic action and dropped beams. On the other side, let's say that this layout will provide some partially some stiffness and some resistance. With dropped beams, it will be not so much. So typically this frame will have to be considered as a secondary frame, if possible. So most typically I will have to have dropped beams in both directions, columns which are oriented in this direction or in this direction, trying to have a balance, so to have more or less an equal distribution of columns in direction X and in direction Y of my building. So it's important to think in this way. So we don't have to think only at the static resistance of the structure, we have to think at the seismic resistance. What was decided to do in this case? So let's make an assumption on the floor depth. This is unidirectional, so you see that there is a direction of application of the load. I did this way because this is what typically is done in Italy. So let's say that the red and blue column are the seismic beams, and so the red and blue parts are the seismic frames, so the primary frames. All the remaining part of the building will be designed to be secondary. So the three columns will be considered secondary columns, and the beams connecting will be considered secondary beam. Of course, we will have to check here what is reported in red, so that all these secondary elements are not contributed by more than 50% to the overall stiffness of the structure. So let's see our example. So we have two floors, the intermediate floor and the last floor, which are different in terms of loads just because of the live load. Let's say this is the typology of floor which I'm considering in this example. So there is a, let's say, a direction of, it's a unidirectional floor, a main direction of application of the loads deriving from this floor. Then I have just given an indication of the no structural loads, yes, and the live loads at the different stories. Of course, as you see, the snow load is very small compared to what you will have in Latvia. So in Latvia, probably it will be 4 or 5 times more than this. Okay, these are the spectrum. So this example is carried out in Italy as we are designing the structure in Italy. In Italy, we have 4 different spectrum that you see here reported, from the operational to the collapse prevention. Let me underline that we will design considering the design-based earthquake, so the life safety one, so the one that you see here highlighted in yellow. I left you also 2 links. Yes, this is double, so this is the link to the website of this morning. Basically, you can also find website for the automatic calculation of this spectrum, so it's nothing too complex to be done. Okay. So this is the shape of the spectrum, the elastic spectrum. We will have also to calculate the inelastic spectrum. Our soil is a soil type B. So basically, the spectrum I've reported before are based on this hypothesis. So type 1 spectrum, soil class B. The building is designed in the campus of the university, so it's a building which has a higher importance. So normally for higher importance classes, we have to apply a factor to increase the PGA, so the peak ground acceleration that I have to use in design. So I have to scale up a little bit the response spectrum. Okay, so normally this factor, according to current version of Eurocode 3, for importance class 3, where schools, universities are falling, basically it is equal to 1.2. Okay, this is just an amplification. So these are the typical load combination for the ultimate limit state, for the serviceability limit state. Basically, in case of a seismic event, this is the typical combination that we have to apply. So pay attention that we have to combine always part of the seismic action in the X direction with part of the seismic action in the Y direction. Let's see now something about the preliminary sizing of the element. So if I'm not defining the size of the element, then I am unable normally to performing the structural analysis. So first of all, I have to define the size of the structural element. So let's start from the secondary elements. So from the beams and the columns, which are part of the secondary framing of this building. So the hidden beams and the gravity columns, let's say. So I left you in this slide a little bit of calculation. So it is not necessary that now I explain you how to derive these loads. You know it better than me. Of course, for the gravity element, what we have to do is a typically gravity design. So we will do a combination of the loads to maximize the bending moments in the internal supports and in the spans. Basically, to design this as you usually design for an element which is designed under static loads. So we will take the action, check the resistance. Of course, if we want to design these beams, in this case, this is designed as a hidden beam because we don't want this to be part of the framing. So the height is fixed. And here you find very typical formula for the design under bending. So basically, we can write a translational and rotational equilibrium here, assuming a certain depth of the neutral axis. In this example, so since this is this is not a part of the primary framing, we have assumed a non-dimensional neutral axis equal to 0.6. So basically, the width of this secondary beam, which is a hidden beam, is 1 meter. So it's 30 centimeters by 1 meter. We find another example here for another beam. So this is let's say the longitudinal internal beam, which still has to be designed according to a gravity load criteria. And basically, based on the bending moment, so comparison between action and resistance, we are able to define the width of this beam. That will be, therefore, 30 centimeters high by 60 centimeters of width. I don't have to explain you. I had more slides about this, but I removed because basically, this point, we are able to define all the sides of all the internal beams of our frame, which are reported here for your summary. We still have to design these columns. So columns 7, 8, and 9. This is the second stories. So for the design of the internal columns, we do as you do in gravity conditions. So basically, we take the actions which are coming from the beams which are applied on the column. We estimate the load. Once we have estimated the load, we have just to design the column cross-section. So we fix one dimension to find the other, for example. So, for example, here we fix the width to 40 centimeters to find the height, which is 50 centimeters, to reach a target value of the non-dimensional axial load, which is, in this case, assumed to be 0.65, because these columns are not part of the primary framing. Okay, so this is allowed in this case. This is another example for column 8. And this is another example for column 9. Consider that, as you see here written in these notes, that you will find when the Normans and Jans will distribute to you the presentation, we try also with the secondary framing to maintain a symmetry in the structure. So even if strictly looking at the axial forces, some of these elements could be smaller, in reality, it is necessary, and this is better, to think always at the seismic behavior of the structure to keep symmetry. Okay, so column 9, even if it is carrying less loads than column 7, it is designed to be equal, to keep symmetry, not because of static consideration. Now let's look at the seismic resistant part. So the primary beams and columns. We have to design initially the sides. We have to define initially the sides also of these elements. So let's say that in the preliminary stage, we can assume that the center of mass is coincident with the center of stiffness. So they are both located here in this point. We will see that in the seismic analysis, we will consider also some eccentricity that in this moment is neglected. So let's focus on one of the two frames as an example. In reality, the other frames will be equal because we have in each direction two frames and the size of the elements will be the same because the design forces will be the same. So let's think, for example, at designing this frame in the X direction. So let's make a summary of the masses, the spectrum, the forces, and so on. So as you see listed in this slide. So first of all, we have to define the masses because we are interested in the seismic forces. So let's consider the loads in the first and second story of the building. This is the one that I've listed before. The loads in the top story of the building. And let's estimate the total masses. So we multiply these loads by the area, okay, to get the total mass of the framing. Of course, for the first and second story, more or less, we will have the same masses. For the third story, this mass in this example will be a little bit lower because we don't have partition walls, we don't have claddings in the top story, and we have snow load, which is considered with a lower contemporaneity factor in case of seismic action. So starting from this mass, if we multiply this mass by the spectral acceleration, we will get the design forces. So here there is another note that you can see in this slide. Let's say that the period is initially estimated with an approximate formula. So the one which is given in current version of Eurocode 8. Probably this will not appear in the new version of Eurocode 8. This is a very simplistic formula because this is just based on the height of the building and the typology. So it's not making even a difference between the typology of framing or if there are walls and so on. So expect that this formula is giving an estimate of the period, which is a guess, a first guess. But when we perform more advanced analysis, we will have to update this period. So it will be trial and error. As we will see, the structure in the final solution will have a period of about 0.7 seconds, not 0.5. So in the spectrum that you see here, I have reported now, just to not to make too many confusion in these slides, directly the design forces related to the period equal to 0.67 seconds. Yes. So the base shear force will be the total mass of the building. So we have to sum up the three stories multiplied by G, multiplied by the spectral acceleration, sorry, 0.37 G is the spectral acceleration, divided by a behavior factor, which is here reported, to get the inelastic force demand. How this behavior factor is determined? We should enter into the code in Eurocode. In Eurocode, it is allowed for moment-resisting frame made of concrete currently to apply this behavior factor, which is reaching 5.85. But we have to remind about something. So the behavior factor cannot be so large because if I take the spectrum, the yellow spectrum, and divide by 5.88, that you see here with this dashed line, this spectrum will fall below the operational limit state spectrum. So it is not possible for sure that the structure is damaging already at the operational limit spectrum. So I cannot design the structure for such a low resistance that will be limited to this value of the spectral acceleration. So my suggestion as an alternative criteria to be sure that you are not using a behavior factor that is too large, just make the ratio between the spectral acceleration for the elastic spectrum at the life safety limit state over the spectral acceleration that you have for the elastic spectrum at the operational limit state. Don't take a behavior factor which is larger than this. This is the criteria applied in this case, which is leading to about 3.88, which is quite large, but is not so large that the structure would result already damaged in the operational limit state. So let's say that the forces are derived based on this idea. And these are distributed based on the modal shape. So the idea that basically the forces will be distributed linearly, increasing along the height of the building. So we can perform hand calculation, especially if you are not very confident with seismic design. I suggest that you normally do this simple calculation to double check the result of a more accurate analysis. Of course, if you are very expert, you will, at a certain point, you will not do any more these simple checks too much, because you know what are the numbers that you are expecting to have. But in your first trials, please do it. So we can derive easily the action in beams and columns, starting from the shear, the story shear. So we can take the shear in the column. Basically, we can consider that this story shear, since the columns are the same, are equal, will be equally distributed among the three columns. Once we know the shear acting in each of the columns, we can easily evaluate the bending action occurring in the column based on the rules that José was also explaining before. So if we impose the point of contraflexion in the center of the column at the higher stories and a little bit higher at the lower stories, we will be able to calculate the bending moments in all the members of the structure. So we start from the shear, we multiply it by the height times a coefficient, which can be 0.5, 0.3, or 0.7, based on the case by case, sorry. And afterwards, we will, 0.3 or 0.5, and case by case, 0.7 and 0.5, and case by case, we will be able to check by internal equilibrium also the bending moments in the column. So let's say that this can be regarded as something very complex, but basically this is something which can be done in a spreadsheet. So we take the base shear, divide by the columns, get the bending moment in the column, and by equilibrium, we get the bending action in the beam. These are the action which are coming from the analysis, let's say. These are not related to any hierarchy, so let's not make confusion to what I've said before. These are just an estimate of the action in the design load situation. With these forces, so these bending moments, what I can do? I have to define the initial size of the beams. So I apply the same criteria as before. So I write a rotational equilibrium to have a design equation for the height. In this case, what I have to impose is a different ductility, which can be imposed limiting the depth of the neutral axis. Let's say this is a suggestion to be sure that when we are performing the ductility checks in a later stage, we will be able to easily fulfill the checks which are provided by Eurocode. So these are the size of the beams which are coming for these frames. And these are an estimate, initial estimate of the bar, which can be deriving from the seismic load situation. It is necessary and is good if we start to make also in the design phase the check of the bars, because we can at least control if the cross-section has too many bars and so modify accordingly the cross-section. Okay, so let's say that this is an estimate, but this is not the final result of our work. For the columns, basically, let's take the shear and estimate the axial forces in the columns. Basically, what we can do initially is to magnify the action in the columns to account for the hierarchy later on. Sorry, not for the hierarchy, to account for the self-weight of the elements, so the self-weight of the column and so on. Basically, as I said, also the column, especially in the base, needs to be sufficiently ductile. Therefore, it is necessary that the neutral axis is limited again. If we write simply translational equilibrium, we consider symmetric bars in the columns, we can get this very simple equation for the design of the column, and this very simple equation to define the height of the column. So if we fix the non-dimensional natural axis to 0.2, we get a very basic design equation which can be used to define the size of the column. As a suggestion, to respect later on the hierarchy, it is better if the column has not a depth which is less than the depth of the connected beam. So in this table, you see a summary of the design of the columns of our perimeter framing. So this is the final configuration. At this point, we have done a good part of our job because we are ready to perform a structural analysis. So this is the layout in the two stories. So when we perform the structural analysis, let's remind that we will, at a certain point, maybe not immediately, but now I'm showing this to you immediately. Let's remind that we have to control that the stiffness of the secondary elements is not affecting too much the overall stiffness of the structure. So we will have to perform a comparison between the stiffness of the structure with all the elements fixed and connected, because this is, of course, a monolithic structure. So all the elements will be, in any case, rigidly connected to each other. So in model 2, let's say we have the result of the analysis of the structure, considering the structure fully fixed in the beams and in the columns. In the model 1, we have the behavior of the structure where the beams and the columns are hinged, as you see here, as they are not contributing to the overall stiffness of the structure. So, I am calculating the displacement and evaluating the stiffness, but a simple way could be also to perform a model analysis to evaluate the periods of the structure. So, if we compare the periods of these two structures, basically the ratio of the periods will be a function of the ratio of the stiffness because the mass is fixed for the two models. So to control if the difference in the stiffness is not larger than 50%, what I can do is compare the periods, the first periods of the periods of the first two modes in the transversal and longitudinal direction. Okay, so T1 and the T2 that you see here. If they are very close, this means that basically the influence of the secondary framing is not very relevant. The question the answer to one of the questions that Jans was doing this morning is that remember that when we are performing a seismic analysis, we will use a 15% reduction of the elastic modulus of concrete. So cracking is approximately considered in seismic analysis by means of this reduction. It is a bit of an approximation, but is what Eurocode is allowing to do. It is very simple to do. So everybody likes to do in this way. Okay, so let's say that to maximize the action of the primary framing, normally we have to neglect the action, so the contribution of the secondary framing. So consider basically the hinges in the column and in the beams just for this part of the analysis, just to estimate and maximize the action on the primary framing. So I would like to say also that I will be glad to share with you the model, the SAP 2000 model of this framing, so that you can look into the analysis and see by yourself also the load combination and what was done in this model. So of course we have to input all the cross section, and afterwards we have to define the load combination. So for the load combination, you will be very, very surprised to know that the seismic load combination which have to be considered are just 32. This is not one, they are 32, because we have to consider the contribution of the accidental eccentricity and the contribution of the contemporaneity between the two directions of the seismic event. So X will be always combined with plus 30% of the seismic event in the other direction, Y, and also the opposite. So as you see, here is just a list of the combination. This is a short video that was prepared by one of our students to explain what are these 32 combinations. So we have to combine seismic event in X direction in that point. So notice that, sorry, I want to explain it better. Notice that normally we don't know exactly what is the distribution of the loads applied on the structure. And also the stiffness is not exactly symmetrical, even if it is symmetrical, because there are uncertainties in the material and in the execution. So normally we will have to consider that there is an eccentricity, accidental eccentricity between the center of stiffness and the center of mass. This, even if the building is symmetrical, will lead to some eccentricity. This eccentricity is considered to be the 5%. So the 32 load combination that we have to consider are with the seismic event in the x direction, plus the 30% in the other direction. And we have to consider two positions of the force acting in the x direction. So this will be the first 4 combination. So then we have plus x, again, the same 4 combination, but with minus y, 30% y. These are the other 4 combination. And then we have to continue because we will have minus x and plus 30% in the y direction and the opposite. So other 4 combination that you see here, minus minus at this point, every time applied in 4 different points. So this is the problem. The same will have to be done for the y direction. So we have 16 combination, let's say, with the main action in the longitudinal direction of the building, and other 16 with the main action in the transverse direction of the building. Okay, so in total there are 32. So this is a thing which I don't like too much. Nobody likes too much, but we are lucky because if we are designing with the software, this is something that, of course, it is addressed normally, typically within the software. So this is a summary of all the load combination, just for your reference. So you have also the video which is showing. So let's say that at this point we will run all the analysis, all the simulation. These are the 3 modes for the building. So in the X, Y, and torsional mode, if the building is regular, we have to expect the modal participating mass mostly in the first 3 modes. This is what is happening for this building, which is regular in plan and elevation. And this is just for your reference, a check of the P delta effects, so for the second order effects, but as it was highlighted by José, this normally will not be very critical for concrete. So as you see, it's quite far because 0.05 versus 0.1. So normally second order effects check are not very important. So once you get the result of the full analysis, of course, this is an envelope of the ultimate limit state seismic combination. Please make a comparison with the simplified calculation. Of course, you don't have to expect the results are the same, but they can be regarded as similar. Of course, there are some variation. But of course, if we compare, for example, the bending moment at the base of the column, so the scatter is not so large. Or if we compare the bending moments in the beams, for some there is a higher scatter, but they are comparable in any way, okay? So of course, there are some differences. One of the main difference between the hand calculation and the accurate modeling, for example, is that also the frame out of plane gives some contribution. So normally, as you see here, the bending moments are a little bit lower than the one that I was considering in the simplified calculation. Then just a few words, and we are almost done, about the design of the elements. So I'm just going very quickly because for sure you know already how to design a beam. It's not necessary that I explain to you how to design the reinforcement of a beam, but I will leave for your reference all this information in the slide of this presentation. So let's say that in the seismic, what I want to give you more is the idea that we have in seismic design. So now that we have the action coming from the analysis, we will take this action for the beam. So this is the envelope taken from SAP 2000, and we will design the reinforcement in the beams. Very, very important. We don't have to over-design the beams in this phase. If we over-design the beam, all the cost of the structure will increase immediately because then I will have to apply hierarchy. So let's try to define the minimum reinforcement. So with a safety factor, which is not so large here in this case. Okay, so for the seismic, we have to limit the resistance of the cross-section. So it doesn't have to be much larger than design action. These are, for example, the layout of the bars in the 3 stories of this frame. Afterwards, we have to design the transverse reinforcement. So I don't care about the methodology. that we have to use to design the stirrups. It is the same that you use normally for designing the stirrup of a concrete beam. What is very important to remind is that here the shear doesn't have to be taken from the analysis. I don't have to make this mistake. I don't have to take shear from the structural analysis of the frame. Since I am designing by hierarchy, I have to apply bending shear hierarchy. So I have some loads which are applied on the beam, but I have to consider the instant where plastic hinges are forming in the beam. So at the end of the beam, there will be not the bending moment coming from the analysis, but the resistance of the beam magnified by an overstrength. So the shear will be derived starting from this equilibrium. The right one or left one, which are for the two direction of the seismic forces. Okay, so this is very important. Once I have the shear, so this is, let's say, just a diagram of the shear force on the whole structure. Of course, I have the shear force in the seismic combination and also the shear force in the gravity combination that will come from the structural analysis. So just the black one is coming from the analysis, the other are coming from the hierarchy criteria. When I have this action, I will have to design the stirrups of the beam. So I will design the stirrups as I normally do for a normal reinforced concrete structure. Just the way I'm defining the action is different. I have to remind that I have certain rules, which are summarized in this slide, for the stirrups in the critical region. So this is the region of the beam which is expected to damage under a seismic event, to provide the ductility, to provide local ductility for an extension which is equal to the beam depth or 1.5 times the beam depth. I will have to increase the stirrups to increase confinement. So I have a number of checks to be done, but these are just geometrical consideration, is not related to some analysis, to provide ductility in these regions. This ductility will be controlled indirectly with this type of controls and also directly performing a comparison between the ductility demand and the capacity. The ductility demand according to Eurocode 8 is just calculated starting from the period of the structure and the Q factor. The larger is the Q factor, the larger will be the demand imposed to the structure, the local demand. So this is what you see here. The local demand, so the ductility of the plastic hinges will have to increase as long as Q is increasing, the behavior factor. So we get this type of formula based on the period. Typically in the frame we can be more in the first case. Basically, this demand, in this case is 10, has to be compared with the capacity. This example, just to be quick, I could also use some more accurate methodology. We see that the capacity of the beam is larger than the demand by 8. So it's very, very large. But this because initially when I was designing the cross-section, I was taking care about the definition of the neutral axis in the design of the beam depth. So just to say, you have worked example at this link as well. So you will have the slides, but you have worked example about the Eurocode at this link of a reinforced concrete frame. You will find a table which is summarizing all the limits for seismic region in terms of longitudinal bar and transverse bar, and all the design equation that I have to apply in my project for the design in seismic region. So all the geometrical limitation and the design formula. So I also pleased to leave you this link. So for the columns, just a few words and we are completed. I will stop in very few minutes. I hope to have still some time. Eurocode 8, to avoid making complex calculation, is recommending to account for the biaxial bending. So or we perform the biaxial check normally, or we reduce the resistance by 1.43, or we magnify the resistance by 1.43. This is deriving from consideration about the Bressler domain for columns. So basically, this is normally seen to be on the safe side. So basically, we can perform verification along one axis, considering also the bending in the other axis, just by means of this simplified criteria So the action in the column will be derived by hierarchy. So magnifying the design forces, design bending moments, by a factor equal to alpha. Alpha will be derived as the ratio between the resistance of the beam converging in a column, in a joint region of a column, magnified by a factor equal to 1.3 for giving sufficient overstrength, divided by the design forces. So in the end, if we make this procedure, so we magnified the bending moment in the column by 1.43 to account for biaxial bending and alpha to account for the overstrength we have to provide. Here is a summary we can get for each of the load combination, the combination of axial force, bending moment, and so on. So here it is listed into an Excel spreadsheet. So for the X direction or for the Y direction, depending on the column. Let's remind that hierarchy is waived just at the base of the column and at the top of the building. In all the other joints has to be performed. So this is a layout of the longitudinal bars that will come out from the amplified bending moment. And below you find the idea of the shear design of the column. So we will not get again the action from the analysis, but from equilibrium. Equilibrium considering this time the formation of two plastic hinges in the two ends of the columns. Again, we have some rules to be fulfilled also for the columns. So in critical region, we have a number of restrictions, basically to provide ductility and to provide confinement. So let's say that if we apply all these rules, this is basically a layout of the stirrups that we will get. So much higher stirrups in the end of the columns and also in the joint region, as we will see in 1 minute. Again, check these tables that I leave to you. These are given in this worked example of Eurocode 8 in the document that it was listed in the previous slide. Of course, we have certain limitations to be respected, but these are just geometrical considerations. Also for the column, we have to perform a ductility check at the base of the column. This is expressed by this inequality, which is given in Eurocode 8. Basically, what is necessary to control is that, again, there is a minimum number of stirrups to confine very well the base of the column. You find reference in this slide, and I go just to the final thing that I want to underline, and we are done. So it's very important to address, this is the last step of every design, also design of the joint regions, because we have to be sure that there is no formation of a strut, so no diagonal cracking, and there are no bar buckling. These are typical failure of joints after earthquakes in 2009 in L'Aquila, in Italy. So these for buildings that were designed, let's say, without any seismic criteria in this case. So this is an observation that was done in the field. So the idea is that basically we take the shear forces in the joint and we try to overstrength also the joint. To do so, this is one of the criteria which is given in current version of Eurocode 8. So the shear force acting in the joint, VJED, is equal to gamma RD times the area of the bars, the sum of the area of the bars, which have to be yielded, times FYD. So basically, the yielding of the bars is what will happen in the beam in the seismic loading situation. The shear force is strictly depending on this. So when the bars are yielding, obviously, the corresponding shear force will be governed by this simple equilibrium. So the shear force is basically exactly equal to the area of the bar multiplied by the yield stress. Again, with the safety factor, which is accounting for the overstrength. So to design these stirrups, a first check is this one. So you see this inequality, which is given in Eurocode 8. If you try to design a joint according to this criteria, you will see that this is very conservative, because the shear in the column is not exactly well considered in the design. So as you see, for this example, you get 11 stirrups with 4 legs in the joint, which is something which is totally unfeasible. It's not possible to construct a joint with all these stirrups. My suggestion, if you are designing according to the current version of Eurocode 8, is better if you use these other criteria, which is an alternative to the previous one, which is based for the design on joints on the check of the strut and time mechanism in terms of stresses. It's coming just from the stress analysis of a joint. So it's possible to check the diagonal strut in compression. So this is the case of a joint which is subjected to axial force and shear. So if we use the Mohr circle and calculate the shear, this is the design equation we can get. Normally the strut is very easily checked, as you see here. So we have a resistance, for example, in our case of 2000, about 3000 kilonewton versus the action, which is 855,000 kilonewton. A bit more a problem can be the design of the bars. So to check the joint, also considering the confinement which is given by the bars, so the horizontal stresses. Again, if we take the equilibrium and we try to find a design formula, basically by means of a stress analysis, it's possible to define a design equation based on the formula which is you will find also in Eurocode 8. This is an alternative criteria to the previous one, so you don't have to consider both of them. If we use these other criteria, you will see that you will be able to get more reasonable amount of stirrups in the joint. This topic of the joint is a bit difficult to face, so because it is criticized also by many Italian designers, because typically it's leading to layout of joints which are very difficult to realize on site. In the new version of Eurocode 8, we will find a design model that it will provide more reasonable amount of bars in the joint. So for the moment, this is what we have to apply, but in the new version of Eurocode 8, we will have a more reasonable design formulation, let's say. These are some examples, for instance, of layout of bars within a joint. So let's remind that we have to put also these stirrups into the joint, which maybe if you're not designing in a seismic area is not something which is strictly required, maybe not always required or not at all. Just the last slide about the damage limitation check. This is the example of the damage limitation check for our building. Basically, you see that normally in reinforced concrete structure, we are able to, since let's say the stiffness is within the concept, so the basic concept of the framing made with this material, the this kind of check will be very, very easily fulfilled. So as you see, we have a design drift of 0.0025 versus 0.005. So it is largely checked. So I am done. I thank you, Yanis, Normunds, and Jans very much for this day and giving this opportunity. And I'm really looking forward to your question and eventually to in the future to have other collaboration on the topic with you in Latvia, and very, very happy to do this activity with you.
Yeah, first of all, I would like to say a really big thank you to you, Massimo and José, for this seminar. It was really interesting and educational. And we actually have a lot of questions, so you probably won't end that soon. First of all, I think you provided like very detailed and really nice guideline how to design primary and secondary elements in the building, right? But another concept is about internal walls. Like, can you just put block walls between those columns inside the building, and why the staircase should be separated from the main slab?
You mean concrete walls, right?
Yeah, not necessarily concrete, like masonry, block walls.
Block walls, okay. So when you are so block walls, you mean like as secondary elements or as a main load-bearing element? Because
no, it's just like non-load-bearing internal partition walls.
Yes, this is typically used in Italy as well. So we have masonry partition walls, for sure. So normally these elements are not considered primary elements. They're considered secondary elements, and we neglect them as load-bearing elements. So typically these are neglecting, but it's very important to consider the damage limitation checks for these elements. So that's check that we perform on stiffness. So limiting the drift of the structure within a certain limit, is just conceived to limit the damage into the secondary elements such as partition walls and masonry claddings. So normally if the drift in the frequent earthquake is lower than 5 per thousand, this means that the damage in the partition walls and this kind of brittle elements will be negligible. So this is the type of control that we do on these elements. But we don't account for this explicitly in the analysis, if this was the question.
Yeah, but it's massive. But anyway, but they aren't counting directly by the behavior coefficient that we use in these cases. It's lower down in the sense.
Yeah.
So it's the way. If they are there, they are never considering the analysis, but the behavior coefficients cannot be so high.
Yeah.
Okay, I think we can move to the next question. In Italy, who will be responsible if the building will be unsafe to use after a significant earthquake 5 years after construction? Would it be designer or Mother Nature?
Unsafe. So it's a nice question, especially the way this is explained. So,
but it's not an additive effect.
So who is responsible? Of course, this is a big question. So if we are meaning that the building is like collapsing, of course, this is a responsibility of the designer and of the, how do you call the proof engineer? I don't know, the one who is checking the execution and the design. These are the two figures that for sure get the whole responsibility. So there are a large number of cases in Italy. So you get a lot of time this discussion in the engineering community about engineers that had to defend in the tribunal after some of the earthquakes because of the collapse of some of the building. So in the view of the seismic design code that we have nowadays, I would say that of course if there is damage, nobody can say that this is a fault of the designer because it's within the idea of the code to have some damage in a severe earthquake. But of course, the critical example that we have are examples where in the end people were dying. This is never to happen based on the code. So when this is happening, for sure, there will be problem of responsibility of the designer and the proof engineer if this is related to some problem in the design or also in the execution. In the execution, for sure, also the construction company has a lot of responsibility, especially for what regards the materials and also the execution. So if some details are badly executed, this can be also due to them. So normally it is Mother Nature up to the level of damage. When it is involving also loss of human life, this will go for sure in the responsibility of designers and constructors. So I think this is so Mother Nature will not take a lot of responsibility.
But I think the question was saying if we design for acceleration of 0.2 g, is equivalent to a design 2 times for, or except to have 2 times 0.1 g.
Okay. So if it is going beyond the expectation. So this is also a good question. Yes, you're right. In the sense that we have experience also recent of earthquakes where we had acceleration which are much beyond the expectation. So let's say that the maximum that we consider, statistically speaking, is an earthquake which is occurring about 2,500 years. But it happened even recently to have specific location where acceleration larger than even this value were observed. So of course at that level, really, I don't think that the designer should take the responsibility because that case should be Mother Nature. But one bad event like destruction of a building or collapse or some fatalities will happen. For sure, there will be a discussion in the tribunal as well, I think. So we have to, the problem is not if we are right as engineers or as designers. We need to convince a judge always that we are right. So we have to hope that the technical assessment done in the court will be done fairly, considering this. From my knowledge, I don't know many cases where it was observed a larger acceleration than expected. It was more frequently found that some design were not performed correctly or the execution was not done well. So this is what I could say.
Okay, and I think we can move to the next question, which is maybe partially related. Does the reaching plastic hinge in concrete beams consider best practice? What would be the cost of repairs for such plastic hinges?
Yes, it may look very strange for sure that having this kind of damage is considered the best practice, but it is in the sense that so the idea is more that again we want to preserve the life, not the building. So in this kind of structure, the idea is that that is something which is accepted, maybe not economically the best solution, but I agree that this kind of damage after a very rare seismic event will be eventually very difficult to repair, so or maybe impossible to repair. This is why nowadays there are a number of research, but they are not anymore research. There are also application of a number of resilient solutions that are trying to limit a little bit this damage. So I remember the seismic event in Christchurch. There were a lot of damages and a lot of collapse as well in buildings that were designed according to a seismic compliant approach. So in many cases, even if the building was not collapsing, so exactly as the code is saying, it was observed that the social cost is too high. So we don't have only to consider the cost of the building, which of course is a direct cost, but normally we have to consider also the social cost, because we have recently, for example, in Italy, had the experience of the earthquake of L'Aquila in 2009. In that case, a whole community was destroyed because even the people that survived didn't have anymore the city. So they have to move somewhere else. So there is an interruption of the social life, which is a high cost. So the damage, of course, can be accepted. But from my point of view, this is already becoming a concept which is a bit old style. For sure, in the future, we will go more towards solution that we are not suffering big damages in case of a seismic event. So,
and that's why it's accepted, or starts to be accepted, that the hospitals, for instance, we should prevent such a level of damages, and therefore people start accepting to have more price in terms of structural and isolated systems from the beginning to be able to reduce this type of damages. And also in Portugal, it's the rule. New hospitals should be built based with isolated systems.
This is there are some concepts which are becoming a policy, so a normal policy. So hospital designed with isolators, but also higher important structure, like for example barracks, or there are a number of structures which are critical in case of an emergency, which are designed all to have a very high performance. So many cases the seismic isolator, but they can also be dampers, so like viscous dampers and so on. So elements which are concentrating damage in a part which is easy to replace, we say, or which in any case, maybe in some cases, maybe doesn't have even to be replaced. So this is the idea.
Okay, let's move to the next question. What would be your recommendations regarding precast structures? Are there ways to make precast frame structures more resilient, or simply avoid them in seismic regions altogether?
So, yes. So precast structures are very, very specific as well. So, of course, when we are designing precast structures, we have to think again at the hierarchy somehow. But of course, it cannot be the same concept that we see in the concrete frame. It has to be a little bit different. So let's say that normally in these typologies, we try, and this is also reflected in the code, to go more for the idea of dissipating some energy in some connection. So in that case, the design of the connector will be critical to achieve a good seismic performance. So, for example, as I explained a few days ago to Jans, Yanis, and Normunds, we had in Italy the seismic event in Emilia-Romagna, 2015, if I remember well, or 16, and we had a lot of failure of precast industrial building, precast concrete industrial building, because they were designed without any seismic criteria. For example, the beam were just supported by the columns without any connector, so just by friction. So most of these covers were falling down because they were just unconnected. But after that, a lot of research has been done to improve the type of connector. So we have strategies to dissipate energy in dowels, for example, or it can be in some connectors of the facade as well. So I don't think that there is any typology which is intrinsically not seismic resistant. Of course, there is always a strategy to improve the seismic performance and to try to have some ductility if possible.
And we can even have the precasted structure over the isolated systems. It would be a good solution because we solve the problem in a different way. So
yeah,
it's not saying it doesn't perform well. It's very stiff. It creates very high seismic forces. Then we need to be careful on the joints and link to the foundation to avoid problems. But it's not saying it's interdicted. It's not blocked to be used.
Well, if we started to talk about foundations, there's also one question about foundations as well. About column foundation hierarchy. Are foundations designed for the same base shear and resulting overturning moment? Is foundation eccentricity considered?
Okay. Yeah. Of course, there is.
We don't hear you, Massimo.
You don't hear me? Don't you hear me? Can you hear me? Yes.
Yes, now it's better.
So regarding the foundation, if you go in the relevant clause of Eurocode 8, you will see that there are a number of approaches for the design of foundation. So three, if I remember well, at least three. So the most simple one is to design the foundation with the behavior, taking the action with the behavior factor equal to 1. So this is a first approach. So we just take the worst seismic action without, so taken from the elastic spectrum, and we design the foundation.
If for instance, there are piles which are not expected after, is an example.
For instance, yes, this is one of the first
cases,
approaches.
Yeah.
Alternatively, of course, it is necessary to get again. It is necessary to get from equilibrium condition the action which are acting in the foundation. So means when the plastic hinge is forming at the base of the column, we have to take this bending moment and the shear which is corresponding and design the foundation which is with these forces. This is a second approach. And if I remember well, there is a third approach which is more simplified, which is simply taking the design action magnified with an overstrength. Now I don't remember exactly what is the number which is given, which is again very simple because we just perform the analysis and we magnify the action by a factor, which I think is very used in practice as well. But the idea is to have an overstrength also in the foundation, for sure.
Okay, let's move to the question about the modeling. As the modeling possibilities have progressed in recent decades, and as more and more complex structures are being designed, in your practice, would you say are most of your seismic design calculations carried out with 3D model computations, or hand calculations are actually still used in everyday practice?
So I talk about the Italian experience. So, but I think it's a trend, a general trend, since nowadays we are going. So I think that in the forthcoming years, finite element modeling will look something which maybe is doing also the artificial intelligence alone. So, or maybe some kind of virtual assistant we will have to make a design. So, which is bringing the stupidity of all of us to a different level. So we will become more and more ignorant, for sure. 3D modeling, for sure, it is, to be honest, always done in the normal practice, in the normal design. But hand calculation is something which is also always done. And in the Italian code, we have now, since about 20 years, also a specification which is requiring for the engineer always to demonstrate with hand calculation, let's say, to validate the analysis. So here we have to validate the results. So for example, we have to, when we perform the analysis, we have to give a reasoning because we have shear force in a column at the base of the building. So more or less as I've shown in this simple calculation. And in any case, let's consider that these simple methodologies, hand calculation, will still be needed to perform easily some pre-design. Otherwise, what we do, just trial and error with the computer. I don't think this is the good way of designing a structure. So it is always necessary to make by yourself a reasoning. So not taking the result of a software as a black box, which is something that we don't have to do. Otherwise, it means that engineering is lost. So we are not needed anymore. So at that point, it will mean that finite element model will be run by the artificial intelligence, and we don't have to do anything. So it is better if we put some intelligence in the design. So in that part, it will be very difficult to substitute us, I think.
Yes, great. And I wanted to ask you, thanks very much for this step-by-step explanation. But what do you think if we are designing, creating unsymmetrical structure without plastic hinges, with soft story on ground level, and if we are violating all these design requirements, then what beta factor should we assume? 0.8 or 1 or 1.2 or 1.5?
Yes. This is also
something like this.
Yeah, when you don't know what to do, so your structure has no ductility and nothing, the minimum which is normally considered to be within already all the safety factor that we have in the code and so on is just the overstrength. So the factor that José was showing this morning, QS, which is 1.5. So less than 1.5, no structure is less than 0.5. Also measure in Italy, typically in the worst case scenario is considered 1.5 for the life safety. Okay, so is the minimum.
Okay.
So this also means that when you see in the table 2, it is not so better than 1.5. So it is a bad number to already know. So when we were talking this morning about flat slabs, it is very close to something which has no ductility. So 1.5 is so if you use 1.5, nobody will say that it is out of the code, out of the scopes. Ideally, of course, Q equal to 1 is corresponding just to applying the elastic spectrum. But 1.5 is reflecting a minimum of overstrength or a minimum of ductility, that in any case, your structure, even if it is not seismically designed, will have.
Assuming damages.
A little bit.
Yeah, we should stress this because it's a concept that...
a little bit of damages. Yeah. 1.5 is just a little bit, but that it is that little bit that any structure can take.
Clear, thanks.
So, and to be clear, what will be your recommendation for, let's say, 5-story building? What is the best strategy? Is to use several cores and like columns, or not just share walls and columns? What's your opinion?
You mean depending on the height of the building, you think? If I understand. So I think that for few stories, it is very popular to use frames, at least in Italy. So up to 5, 6 stories, steel frames are used. If we go for higher buildings, I think it will be necessary to have for sure walls. So you must have some kind of bracing. So normally in concrete we use walls or cores. So clearly, if we are talking about a medium height building like 15, 10 stories, it will be needed to have some walls and some cores. Otherwise, it will be very, very difficult to have the sufficient resistance for the horizontal forces. So,
or we get such a high level of reinforcement that we say, okay, it's no way. Yeah? So it's.
But it's the same idea, so it depends on your experience, but it's same thing with steel. Frames can be used up to a few stories, at least if you don't want to have a jumbo cross-section that maybe in the United States is also done. But starting from, let's say, medium height building, 10, 15, that point it will be needed to have some bracing. So it will become a problem of also of drift at a certain point of stiffness. So you will start to have P-delta effects. You will start to have problem in complying with the lateral stiffness of the frame. You will get high reinforcement if we are talking of concrete. So walls at a certain point will be needed for sure.
Today we have talked quite a bit about concrete structures and steel structures, but how about timber structures in seismic regions? Are they feasible, and are there any benefits for using them, like CLT buildings, for example?
You already know the answer, right, Yanis? So he's almost a New Zealand guy. So in New Zealand is very much used wood. So I have a little of experience with wood. Let's say that with wood, typically a framing. So like the concept of the frame is not the most popular thing, because of the flexibility, especially of connection and also of the members itself. But in a seismic area, it is becoming very popular in Italy, the cross-lump, so CLT, as you said. So walls made of wood. In that case, having energy dissipation in the hold downs, so in the connectors. Or the concept which is more similar to the cold form steel of the panel framing, so where you have studs, so very similar to the CLT, to the cold form steel structures. In that case, and also in the case of the let's say massive timber solution, normally the dissipation is in connectors, so hold down or nails. Again, even in these typologies, if we are starting to allow damage, this structure will suffer a lot of unrepairable damage after a seismic event, because wood has no capacity to dissipate energy. It is similar to concrete, so it is not so weak in tension as concrete, but still there is not a real dissipation. So there is some capacity to resist in tension and compression, but it is mainly elastic or pseudo-elastic in compression. But to a certain point, let's say that it will fail, the material itself, it will break in a brittle way. So typically we try to find a way to dissipate in some steel parts, again, the connectors they can be. But wood normally have low mass, lower than concrete or steel as well. So this is a good point, I think, of this structure. So for example, this is a case where probably when you start to face the design of a wood structure, if this is 2-3 stories, probably if you design it with a behavior factor equal to 1.5 or 1, you will realize that you don't need to have ductility because the size of the element is already sufficient to resist to the forces. So I think it's more or less my view on this.
And actually, I think there's also a positive effect on foundation loss as well, because sometimes when you go from precast building to CLT building, you can go from pile foundations to shallow foundations, for example. Let's move to the next question from the audience. In slide 16, demonstrated weak joints for hierarchy design. Maybe you can comment something about this question.
Let me see if I can open again the slide. Slide 16, yes.
Yeah, 1.6.
Wait a second, I want to share again. Okay. So this one.
Yes.
This is not exactly about the weak joint. This is a story mechanism, which is mainly concentrating all the ductility demand in one story. So as you see here, it's not the joint which is failing, but it's the column cross-section. So this is a failure of the column in bending. So it's, let's say, itself, the member is also maybe characterized by some ductility, because we see that there is no shear failure, it's a bending failure, but the joint is still there. So it's not a problem of the joint here. I don't know if this was the slide, by the way. Maybe it's another.
Yeah, and there's like a follow-up with a few questions. Would weakening of the beams and their joints improve the situation? And also in that particular situation, should joints have been designed more ductile?
Sorry if I forgot, I lost some parts of the question. Poor hierarchy design, yes, for sure. This is a structure which is designed. So this is a test done in Japan, but is done on a structure which is not seismically designed. So for sure there are a number of problems. The biggest is that there is no hierarchy. So normally we say that in the current codes, the idea is to have a strong column and a weak beam. This is the opposite. It's a strong beam and a weak column. So this is exactly the opposite of what should be done. Okay, so the idea is this is not a seismically designed frame. This is a frame which is not complying with seismic design. So this is, I hope this is what was about the question.
Yes, and this is answer to last one question. Explain why flat slabs are not advised in use in seismic regions. This is the same, which was explained in our lecture that then a column is weaker. Yeah.
So the problem is that with the flat slab, you have a very rigid, strong floor, and then the failure will be probably in the column. So even if a little bit of ductility can be promoted in the slab, based on basically in the new Eurocode there are some rules, but it will be very little, and mainly the damage will be concentrated in that case in the column. So which is not the best for high seismicity areas, and this is why also in the new Eurocode 8, this will be not allowed if you are in a ductility class high, just in ductility class medium or low. So flat slab, I'm not a big fan, but I understand that this is just a seismic perspective. It's not in general, because of course, generally speaking, it's a good typology because it's an easy construction. But for seismic, I don't think it has a big potential to have a very high seismic resistance.
Yeah, but we need to accept that they are very popular. First thing, second thing, the architects and all the services they like because they don't have beams to cross. So the way I see that they can be used more efficient in seismic zones, it's to put, okay, accept the flat slabs, but anyway, consider on the perimeter of each floor some beams. And so you try to have the frames, which are classical frames, beam column, and still use in the inner side of the each floor the flat beams, accepting that these won't work so well for the horizontal forces created by the seismic event. It's the way I see that we can solve or minimize the problem.
Yeah, this is a good way, but you are changing a little bit the typology, let's say.
Of course, I'm proposing something which we know that works better. And there is another question here, Massimo, which is interesting because it's relating to the length of the piles to reach to the depth of the good foundation.
The last one, yes.
Yeah.
In the case study, how would this one, right? Would the
Mhm.
design be affected if there was no basement? Would you still place foundation at 5 meters depth?
Mhm.
If not, what would be the procedure?
Mhm.
Or what will be the effects of placing the foundation at only 1-2 meters depth?
Mhm.
Okay, that soil was fill dirt. So probably, of course, if you want to do it, you should have piles.
Or a
to reach
foundation slab. Huh?
oh,
Yeah.
maybe, but on fill dirt.
Uh-huh. No,
I
I
don't
wouldn't
know.
put it, but anyway, I would clean it everything up to the 3 or 4 meters and then.
Let's say that in this case it was a quite easy decision because let's say that this building is close to the street and the street is at that level, and so it's automatically necessary to have this partially under the ground level. If you don't want to do, you have to use piles or, as you say, foundation slab, but maybe piles, short piles, at least short piles to reach a better soil. How the design will be affected? In no way, because we usually don't consider the soil. So of course in theory, there is a big problem of soil structure interaction, especially when you have piles, especially because piles are in part also damping some of the energy. So there is some kind of damping which is related to the pile and the interaction of pile with soil. But this is totally neglected because normally we always design with the full restraint. So for the superstructure, there is no problem. So the design will be the same independently from the type of foundation. But this is on the safe side because, of course, as long as we increase the stiffness, placing the fixed foundation, and we neglect the damping of the piles in the soil, this will be for sure on the safe side. And this is the assumption that is typically done. But with this, I don't want to say that in a more advanced approach, it's not possible to account for this damping. Years and years ago, I remember I had a design of a much bigger structure with a lot of piles, and it was considered the idea to evaluate the real stiffness of the piles, vertical and horizontal, and also the damping. So there is the possibility to design this foundation and also seismically design the building, placing equivalent springs, simulating the pile, also considering the interaction between the piles. But these are we are going in geotechnical and in very complex geotechnical. So there are a lot of studies, I think, about this, also with very complex discrete element method. So it's a bit complex. But for everyday design, I think place the full restraint and don't think too much of the foundation. You will design the foundation in the second step of the analysis.
Yeah, or
Okay.
go to the good depth, and even if you don't have the -1, or execute the foundations at the level that you need to have a controlled and short foundation. So if it's up to 5, 6, 7 meters, I think a direct foundation at the good level should be the best solution.
Yes, for sure.
Okay, thank you very much. I think we answered all seismic questions. There are one question.
Thank you, José. And And it was very useful, very useful overview of seismic design, of seismic structures. I hope that will help Latvian engineers to get a better understanding about seismic questions. And yeah, thank you very much. And I hope we will meet you in the future.
Thank you to the audience, and so let's keep in touch for other things. And if you need, just you have the reference in the slides, and please contact us. We are very happy to help you, and also through Normans if you prefer. And there is no problem for both of us. Thanks to everyone.
Okay,
Yes.
thank you very much.
And
Thank
it was
you.
a pleasure. It was really a pleasure.